Yeah, good morning to one and all. Today we are going to see the basic concepts of fluid mechanics. The outline of this lecture is the fluid mechanics, overview of the fluid mechanics, characteristics of fluid, measures of fluid mass and weight, viscosity, compressibility, vapor pressure, and the last is the surface tension. Now, fluid mechanics overview. Fluid, the fluid is divided into two types. One is gas, liquid. Gases are, we all know this, gases may be of helium, nitrogen, etc. Liquid, it might be of water, oil, alcohols, etc. And water, again, some of the properties of water are the compressibility, density, viscosity, vapor pressure, surface tension. Now comes the mechanics of fluids. There are two different types of mechanics. One is statics and dynamics. The fluid flows, the fluid flow is called as the fluid when it is rest, that is called as statics. That is the force acting on the summation of force acting on the fluid is zero. Dynamics of fluid is when the fluid is in motion, and especially when the pressure force are considered, then it is called as fluid kinematics. Pressure force are not considered, called as fluid dynamics. Statics, fluid statics are again divided into three types: stability, pressure, and buoyancy. The summation of force acting on the dynamics is greater than zero. That is when the fluid flows. There are two different types of flows. One is laminar flow and turbulent flow. That is viscous and inviscid, steady and unsteady state, compressible and incompressible fluid. Fluid dynamics. Some of the characteristics of fluids are the gaseous states and the liquid state. When large molecular spacings relative to the solids, weak intermolecular cohesive force which cannot resist the shear stress in a stationary state will take the shape of this of its container, generally considered as continuum. The viscosity distinguishes different types of fluids. Measure of fluid mass and weight. Mainly, first we'll say the property density. Density is, we all know density, that is rho is equal to mass by volume. Different fluid can vary greatly in density. For example, water will have some density of 1, then mercury will be having a density of 13.6. Then liquid density do not vary much with pressure and temperature. Gas density can vary quite a bit with pressure and temperature. Density of water at 4 degrees centigrade is 1000 kg per meter cube. Density of air at 4 degrees centigrade is 1.2 kg per meter cube. Specific volume, that is V is equal to 1 by rho, that is reciprocal of the density, that is 1 by density, that is reciprocal of density. Then next comes the specific weight. The specific weight of the fluid, its weight per unit volume, that is rho is equal, that is specific weight is equal to rho into g. G is the acceleration due to gravity, that is of 9.81 meter per second square. Specific weight characterizes the weight of the fluid system. Specific weight of water at 4 degrees centigrade is 9.81 kilonewton per meter cube. Specific weight of air at 4 degrees centigrade is 11.9 newton per meter cube. Measure of fluid mass and weight, that is specific gravity. Specific gravity is defined as the ratio of the specific gravity of any liquid to the specific gravity of water. Gases have low specific gravity. Liquid such as mercury has a high specific gravity of 13.2 to 13.6. The ratio of this mercury is unitless. The density of water at 4 degrees centigrade is 1000 kg per meter cube. Viscosity interaction. Viscosity is the measure of the fluid which is not captured simply by the density or specific weight. A fluid cannot resist a shear. Under a shear begins to flow. The shearing stress and the shearing strain can be related with the relationship of the following form of for common fluids such as water, air, oil, and gasoline. This tau is equal to mu into du by dy, where mu is called as the coefficient of dynamic viscosity of the fluid, u is the velocity of the fluid, and y is the vertical coordinate shown in the figure. Next is the viscosity measurement. A capillary tube viscosimeter is one of the methods of measuring the viscosity of the fluid. The viscosity varies from fluid to fluid and is dependent on the temperature. Thus, the temperature is measured as well. The unit of viscosity is Newton second per meter square. And here the dynamic viscosity can also be represented as 1 poise. 1 poise is equal to 0.1 Newton second per meter square. The difference between Newtonian fluid and non-Newtonian fluid. Newtonian fluid is a fluid that flows in a straight way, a non-Newtonian fluid which does not. Non-Newtonian fluids are non-linear between the stress-strain relationship. Newtonian fluids are linear relationship between stress and strain. Most common fluids are Newtonian fluid. For example, water. These are the Newtonian fluids. For example, this is the Bingham plastic for toothpaste, and for latex paint, then the rate of shear strain will get increased. Then for cornstarch, it is a bit low. Now comes the viscosity, that is kinematic viscosity. Kinematic viscosity, V is equal to mu by rho. We know that mu is the dynamic viscosity. It is represented by poise, and rho is the density. Kinematic viscosity is another way of representing the viscosity. It is also used in the flow equation. The units of this kinematic viscosity are L square by T, or meter square by second, or feet square by second. Compressibility of fluid. Compressibility of fluid and bulk modulus. Bulk modulus is defined as the increase in pressure to the bulk modulus is defined as the ratio of increase in pressure to the decrease in volume to the original volume. That is, bulk modulus is represented by the letter small k. K is equal to dp by d rho by v, or dv by v. dv is the decrease in volume, and v is the original volume. Compressibility is the reciprocal of bulk modulus. Measure of how pressure compresses the volume and density. The unit of bulk modulus are Newton per meter square, that is Pascal. The large values of the bulk modulus indicates the incompressibility. Incompressibility indicates the large pressure are needed to compress the volume slightly. It takes 3120 psi to compress a water of 1% at atmospheric pressure and 60 degree Fahrenheit. Most liquids are incompressible for most practical engineering problem. Compressibility of fluids, that is compression of gases. Ideal gas law is P is equal to rho into RT, where P is the pressure, rho is the density, R is the gas constant, and T is the temperature. Isothermal process, that is the constant temperature, P is equal to P by rho is the constant. And isentropic process, that is frictionless and no heat change, P is equal to rho to the power of K, that is equal to constant, where K is the ratio of specific heat, Cp is the constant pressure, to Cv is the constant volume, and R is equal to Cp minus Cv. If we consider air at some condition as water, we can show that air is 15,000 times more compressible than water. However, many engineering applications allow air to be considered as incompressible. Mathematically, this isothermal process can be represented as EV is equal to P, and isentropic process can be represented by EV is equal to K into P. Compressibility of fluids, that is speed of sound. A consequence of the compressibility of fluid is that small disturbance introduced at a point propagate at a finite velocity. Pressure disturbance in the fluid propagates as sound, and their velocity is known as the speed of the sound, or acoustic velocity. Acoustic velocity is denoted by the letter C. C is equal to the square root of dp by d rho, or C can be given as a square root of E suffix V by rho. Isentropic process, that is frictionless, no heat change, because isentropic process can be given by C is equal to root of Kp by rho. Ideal gas and isentropic process can be given by C is equal to square root of K into R into T. Compressibility of fluid, again comes speed of sound. The speed of sound of air at 60 degree Fahrenheit is approximately 1117 feet per second, or 300 meter per second. Speed of sound in water at 60 degree Fahrenheit is 4860 feet per second, or 1450 meter per second. If a fluid is truly incompressible, the speed of the sound is infinite. However, all fluids compress slightly. For example, a jet aircrafts fly at a speed of 250 meter per second at an altitude of 10,700 meter, where the temperature is of minus 54 degrees centigrade. What is the ratio of the speed of the aircraft? V to the speed of sound, C at the specified altitude. Assume K is equal to 1.40. Let's see. Ideal gas and isentropic gas, we know C is equal to square root of K into RT. K it has been given as 1.4. Then R, we know it's 286.9 into J, that is in kilogram per Kelvin, then multiplied by 219 Kelvin. So C is given by 296.6 meter per second. Then compressibility of fluid, again speeds of sound, ratio is equal to volume by C. Ratio we know 250 meter per second, and C we have calculated in the previous slide, that is 296.6 meter per second. So the ratio is 0.84. The above ratio is known as Mach number, that is MA. For MA less than 1, then that is called subsonic flow. For MA is greater than 1, then it is called supersonic flow. For MA is greater than 1, we see shock waves and sonic booms. First, wind tunnel visualization known as Schillerian method. Consideration instigation from jet speed allowing us to see a shock wave. Next is vapor pressure, evaporation and boiling. Evaporation occurs in a fluid when liquid molecules at the surface have sufficient momentum to overcome the intermolecular cohesive force and escape to the atmosphere. Vapor pressure is the pressure exerted on the fluid by the vapor in a closed saturated system, where the number of molecules entering the liquid are the same as those escaping. Vapor pressure depends on temperature and type of fluid. Boiling. Boiling occurs when the absolute pressure in the fluid reaches the vapor pressure. Boiling occurs at approximately, we all know it's 100 degrees centigrade, but it is not only a function of temperature but also of pressure. For example, in Colorado Spring, water boils at a temperature less than 100 degrees centigrade. Cavitation is the form of boiling due to low pressure locally in a flow. Next comes the surface tension. At the interface, surface tension is the interface between a liquid and a gas or two immersible fluid or liquid. Forces develop forming an analogous skin or a membrane stretched over the fluid mass which can support weight. This skin is also called as a membrane. The skin is mainly due to the imbalanced cohesive forces. The interior of the fluid is in balance as molecules of the like fluid are getting attracted each other, while on the interface there is a net upward pulling force. Surface tension is the intensity of the molecular attraction per unit length along any line in the surface. Surface tension is a property of the liquid type, temperature and other fluid at the interface. The membrane can be broken with the surfactants which introduces the surface tension. Surface tension of a liquid droplets. The pressure inside a drop of the fluid can be calculated using a free body diagram. Real fluid, this is for example, if this is a droplet of water, if we are cutting the droplet of water by 2 type, the surface tension interacted is delta p pi into r square, that is the radius of the droplet. R is the radius of the droplet and sigma is the surface tension, and delta p is the pressure difference between the inside and the outside pressure. The force developed around the edge due to the surface tension along the line, that is F at surface, is 2 pi r sigma. This force is balanced by the pressure difference delta p. The F pressure, that is force pressure, is given by delta p into pi r square. There is a mathematical model given. 2 pi r is applied to circumference, and pi r square is the applied to the area. Surface tension and liquid droplet. Now equating the surface tension force to the pressure force, we can estimate delta p is equal to pi minus pe. Delta p is equal to 2 sigma by r, where sigma is the surface tension, r is the radius of the bubble or any droplet. This indicates that the internal pressure in the droplet is greater than that of the external pressure, since the right hand side is entirely positive. Okay, is the pressure inside the bubble of water is greater or less than that of the droplet of water? You can prove by yourself by following the result. Delta p is equal to 4 sigma by r, where r is the radius of the droplet or any solid bubble. Surface tension and the capillary action. Capillary action in a small tube which involves a liquid gas solid interface is caused by the surface tension. The fluid is either drawn up the tube or push down.